don't get it. Maybe I never got it open. Okay. Anyway, it's Fun with Technology Day. Yay! I'm glad you like it. Okay. STP. Okay, I found it. Okay, so chapter 4 is about regression and correlation. Regression and correlation. So 4.1 is linear equations with one independent variable. So what do we mean by that? So lots of relationships in the world can be modeled if you put one variable on the horizontal axis, another variable on the vertical axis, and you get data, and it turns out to be linear in nature. The data turns out to be linear in nature. That's not all relationships, but many are like that. So here's 3 examples. So this is, here on the x-axis is the year, and then on the y-axis, the vertical axis, is the world record time in the mile. So from 1910 to about 1977 is where this data is. World record times in the mile came down like in a constant rate, right? They came down at generally a constant rate for those, whatever, 60 or 70 years. Okay, this one here is for some store, some video game store, number of games rented at the store, and your total cost for renting that many games. So the more games that you rent, the higher your cost, and that's in a linear relationship or with a constant rate of change. Okay, and then this one is time in days, and then grass height in meters. So evidently they planted some grass, some different grass samples. They let time go by and they measured the height of those grass samples. And as time went by, they saw that for about 2 weeks, the samples generally grew at a constant rate. Okay. So lots of relationships of 2 quantities in the real world can be modeled linearly, okay, with a line. Not all. So there's lots that aren't, too. But this is one common relationship between quantities that shows up in the real world. Okay, and so the equation of the line is y equals b naught plus b1x. That's their version of this. Okay, so b naught is the y-intercept. And b1 is the slope. So let's go back and analyze the ones that we already looked at in terms of this idea here. So we're saying that y equals b naught plus b1x. Okay, so let's look at this first one. So if I were to kind of guess, so I'm just kind of throwing that on there. It's not perfect, but what would b naught be, and what would, so we're saying y equals So we said B naught was the y-intercept. So what is the value and what does it mean? All right, he wants 259. Agree with that generally? Okay, and so what does it mean? So what? How would you interpret what that value is? 259. So actually, we need a new scale down here. So we need so this our x is going to be number of years since 1910. Okay, number of years since 1910. So how do we interpret that number 259? What does the number 259 mean?
It's time in seconds per mile at 1910. It took people 259 seconds to run it.
That was the best time.
Yeah.
That was the best time. So 259, that's seconds. And so, yeah, it's the value of this y variable when x is 0, right? So, yeah, in 1910, the world record was, actually, let's more like 258. So the world record was, say, 258 in 1910, or when x equals 0. So that's what B naught is. The y-intercept is what you get when x is 0, right? It's what you get for your y variable when your x variable is 0, and it's called the y-intercept on the graph. Okay, B1. So B1 is the slope. Okay, and so to get slope, what is slope? Slope is, we talked about delta in this class, right? At some point. Delta means change, right? So the change in y over, so it's how much the y variable changes for some change in x. So let's look right here. So we need to calculate that we need 2 points, right? So let's say this is 1 point, and another is, we'll just use this one right here. Okay, let's make things nice and easy. Okay, so how much did y, or the time in the world record, change for those 2 points? So let's write ordered pairs here. So we write ordered pair for that point, write an ordered pair for that point. So what is that first ordered pair? So x and y. What's that first ordered pair? 20 and 250. And then later here, what's this ordered pair right here?
60.
And 230. Okay, 60 and 230. So what was the change in y, and what is the change in x? Change in y is 20. Agree with that? You said negative. Is it 20 or negative 20? That makes a difference. You're changing to negative 20 now? Negative 20? Right, it's going to be final minus initial, right? And the change is negative because why? Because y is going down, right? So as time goes by, people run faster, and so the world record time goes down. So we want final minus initial, and that's going to give us a negative 20. So final minus initial. And what's the change in x? That's easy, right? That's just 40. So you do final minus initial y and final minus initial x. We get negative 20 over Okay, so what in the heck does this mean? What does that number mean in terms of the quantities, right? In terms of the world record per mile and number of years. Can anyone interpret that? What does that mean?
Is it that for about every 2 years, the mile time goes down by a second?
He said for every 2 years, the mile time goes down by 1 second. Is that what that number is saying? She likes it. So this would be a change in, she's saying this is a change in number of years. If 2 years go by, change in x, then the mile time comes down, -1, it comes down 1 second every 2 years. Yeah, that's pretty good. Or how about per year? How much does the mile time come down per year? Half a second, right? And how much does it come down in 10 years? How much?
5 seconds.
Yeah, so this also would tell you that in 10 years, it comes down 5 seconds, right? So given any change in number of years, how much does the time in seconds change? Given any change in the number of years gone by, how much does the time change? How much does the world record time change? So we said in 1 year, it comes down a half. In 2 years, it comes down 1. In 10 years, it comes down 5. So given any delta x, then what does this number tell us? That the change in time is? Yeah, it's -half times whatever change you selected, right? So it says given any change in time in years, to get the change in miles per second, you would multiply that by -1/2. So if 2 years go by, multiply by -1/2, the mile time comes down 1 second. If 10 years goes by, multiply by -1/2, mile time comes down 5 seconds, -5. So given any number of change in years, the change in the world record is -1/2 times that change in years. Does it make sense? So in 6 years, how much does the world record time come down? 3 seconds, right? So 6 times -1/2 is -3. So in 6 years, you expect the world record time to come down by 3 seconds. In 20 years, you expect the world record time to come down by 10 seconds. That's what the slope value means. So this is the slope, and this is what we call the rate of change. The rate of change. Okay, put it all together, and you get the equation of this line. So what's the equation of this line? Y equals 258 minus 1/2 x. Okay, any questions on that stuff? So let's have you give it a shot here. You practice on the video game example. Nice easy example. Okay. So I'm going to give you your list of tasks here. Can you still read the numbers for the video games in the back? If I have it that size? Okay, so here's your list of tasks. Let's first. So first task, define the meanings of X and Y. Find the value of B naught. And interpret with a sentence. Find B1 and interpret with a sentence. Write the equation of the line. That's good for now. So 4 tasks. Define the meanings of X and Y. So you're writing out words. What does X represent? What does Y represent? Find the value of B naught. Interpret B naught with a sentence. Okay. Find. So what is the Y-intercept? Y-intercept is 20. What does it mean? He's asking if that's how much it costs when 0 games are rented. Yeah, so if you before you rent any games, when you've rented 0 games, if you want to rent from this company, you have to shell out $20 to get a membership or something like that. So it's like it's the cost you pay before renting any games. If you want to rent games from this store or this website or whatever it is, you have to sign up. You have to pay $20. So then from there, then your cost goes up from there based on how many games you rent. Did that answer it? Yes, it's the cost you pay when you rented 0 games. So it's some kind of startup fee or membership cost, right? Okay, other questions about this? Can we go on? All right, so what did we have for this, our line here? I can do it. Did we have 258 plus or minus 1/2 x? So what do you know? There's something different about one of these 3 from the others. So other than the fact that one has a negative slope, it's going down. These 2 go up. That's obvious. But another difference, that one of these is different than the other 2. What do you notice? Scatter plot? What were you going to say?
I mean, I was going to say that the video game one doesn't have a starting x-axis or y-axis defined value, and the other 2 will do.
It just inserted 0 though. Because then the third one, it doesn't really start at 0, it doesn't have a y-intercept, that's the one that's different.
Yeah, I would guess. Okay, so all right, I'm thinking about something different than that. That's good. Okay, but I'm thinking about something different. What one of these is different for another reason? Which one is it?
The video game one is the only one where all the plots are exactly on the line points.
Right. Okay. Do you see that these points are exactly on this line? Where this is what someone said scatter plot. A scatter plot is where you take real world data and it generally forms the trend of a line, but not exactly, right? So that these points aren't exactly on a line, nor are these, whereas these are exactly on a line. So with regression analysis, that's what we're talking about. We're talking about looking at the trend and coming up with what's called a best fit line. Best fit line. So with a video game example, we don't need a best fit line because there is exactly a line, okay? If they charge so much per game rented, then your charges for a number of games rented, they're going to just fall right on the line. But why? Because they've set up the scenario before the data, right? They set up the scenario in a linear fashion before the data is taken. But if we just take data from the real world, this is often what happens. We get a linear trend, but the points aren't exactly on a line. So we want to come up with this line. That's kind of what I did by sight, right? I just kind of drew the best I could through the points, and we came up with this equation. So this is not, there is no true line through those points, but it's something like a best fit line. So the point of a best fit line is to make predictions. Now we can use that relationship to predict if that trend continues, what would be the mile world record in 1990? So again, this was 0, right? 20, 40, 60, 80, 100. So we can use the line now to say, if the trend stayed on the same trend, what would we expect the world record time for the mile to be in 1990? How would we do it? What would we say? He said plug 90 into the equation. Is that right?
80.
Yeah, so when 1990 is what x value? So 1990 is an x value of 80. And so what is this line? This line gives us what every point on that red line, including the one at x equals 80. So when x equals 80, what do you get for y? 218? So how many seconds is that? Or how many minutes is that? Is that under 3 minutes? I don't know if, or under 4 minutes? 3 something?
3.6.
Yeah, I don't think it's come down that far. But if the trend, or first of all, my line is too. Do you see that my line is also sloped too far? It's too steep downward. But just for whatever, for our purposes. So that's the idea of a best fit line, is then you can predict, kind of get an idea of what values would be for data points that you don't have. You see? We could also predict what it was in 1950, right? So we could predict what was the fastest mile in 1950. Well, we'd plug 40 in, right? We'd plug 40 in, it'd be what, 238. Okay, so number 5 on your sheet. How much would it cost to rent 40 games? Okay, how much? What's your cost for renting 40 games? Number 5 on the sheet. Okay, make sure you have your equation right. If your equation's not right, you can't get this right. So you might check your equation with, if you haven't already, somebody else. And I'm saying for number 5, how much would it cost to rent 40 games? Okay, hopefully that was pretty easy. Do we agree? Okay, so here's some examples of some scatter plots. And like I said, not all relationships in the real world turn out to be linear. Okay, but so for which of these would it be appropriate to say, yeah, we could come up with a best fit line? So which of these? The first one. Does the first one? What's that? For the first three up there on the top. So what about this? Is there some kind of best fit line for this? If this was our data? No, it's nothing. You don't want to try to do a line at all because you could make a case for this, but then you could make a case for this. Those are totally different, right? So there's no for the. And then what about this one? No, what does the trend seem to be like? Like a curve, right? So some kind of curve. Okay, so but this one, it looks like it would be appropriate. Let's see if I can do it right through the middle. There we go. Something like that. Something like that would be appropriate to put a best fit line on. The other two not. What about the second example here? The middle one, right? This one curved. This one weird, right? You never have real world data. That would be kind of weird. But so yeah, this one. So again, not all relationships in the real world are linear, but you know, and then some. There's a degree to which it is linear. So, like the ones we saw on the previous page, these both have a very strong linear tendency, whereas the ones we just showed has kind of a less, but still. So it's varying degrees, right? So when we have data, there's varying degrees of how well a line fits the data. So we want to come up with an equation for doing this. So here's 4 data plots, 4 data points that seem to somewhat have some kind of linear trend, right? Up, something like this. So seems like that it would be appropriate for these 4 data points to make a linear trend. So here's two possible lines. 0.5 plus 1.25x, negative 0.25 plus 1.5x. So you see they're both kind of trying to match the data points. Okay, so what we want is the best fit line. So the best fit line is about minimizing the error between the line that you have and the points. So the error is, for each point there's an amount of error. How far away from the line is that point in terms of your y value? So the error for this point right here to the line is -1. It's -1, or it's 1 unit below the line. And for over here, it's 3/4 of a unit below the line. So what we're going to do is we want to come up with some value that kind of totals up all the error. Totals up all the error found between the points and the line and minimizes that, right? So if we have the minimum amount of error between the data points and the line, then we have what's called the best fit line. Okay. So, and it's they don't sum up the error, but the squares of the errors. That's what they do. They say they square all the amounts of errors, and then they add them up, and the one that has the least square is the best fit line. So the least square criterion is the line that best fits the set of data points, the one having the smallest possible sum of squared errors. So they find all the errors, square each one, sum them up, and then whatever line has the least sum of the errors squared is what we call the least squared best fit line. Okay, so the regression line is the line that fits the data points, best fits the data points according to the least squared criterion. And the regression equation is the equation of the regression line. And we've talked about that. This is just the equation of that line. So our criteria for getting a best fit line is the least squares. Least squares, summing up the squares of the errors and getting the least value of those. Okay, so here's those lines I showed you before. So this is the point. This is the y value on the actual line. So that these y values come from the line here. And so they found the difference in the y values from like observed and on the line. They squared them, they added them up. Same thing. They found the y values, the differences between the y values on the lines and the actual y values of the points. Took those e's, squared them, added them up. So which line does a better job matching which one does a better job modeling the trend of the data? Which line, A or B, does a better job modeling the trend of those points? B, lower sum of squares, right? We want the least sum of squares. So can you kind of see that? Can you see that B is doing a better job fitting than A? Yeah, B, it goes more, it's better. So by making that slope a little steeper, or less steep, no, more steeper, right? So B has a steeper slope. It does a better job of going through the points. And here's where the numbers show it, that the sum of the squares is lower. Okay, so here's some data. This is the age and price of 11 Orions. Do they still sell Orion cars? Does anyone know what an Orion is? Ever heard of that? Okay, I have no idea. Anyway, so this is the age and price. So as cars age, they depreciate, right? Price comes down. So here's a scatter plot. Does it look like a linear trend, generally? Yeah, so it would be appropriate to make a regression line for this. Actually, constructing the least squares regression line from a set of data points is a complicated procedure. We're going to let StatCrunch do it for us. So instead, we're going to look at the least squares line, and then we're going to analyze it in terms of the total error. So the normal progression of things is you take the data, and then you come up with the least squares line. We're going to let StatCrunch do that for us. Okay, and then we talked before. All right, so here's the equation of the line 195. Sorry, that's not intentional. So the equation of the line is 195.47 minus 20.26x. In hundreds of dollars. Okay, so basically this is what we'd use to predict. So can we predict the price of an Orion when it's 8 years old? To predict the price of an Orion when it's 8 years old, what would you do? Yeah, so that means x equals 8, right? And we want to know what the y value is when x equals 8. So by substituting 8 for x, so y hat is not a true data value or not a true y value, but it's what the line predicts, right? So y hat is what the line predicts for the y value. So did you find it, Gina? Were you doing that? Not $33. I think they're better cars than that.
Oh, yeah.
33.39.
Okay, but what does that number mean? So we got to interpret what that number means. It doesn't mean $33. The car's worth $33.
33,000.
Yeah, these are numbers in hundreds, so you're going to multiply that by 100. So 3,300 and $39 would be the predicted, right? Predict based on the data after 8 years. If the linear trend continues, we predict it to be 3,339. What we just did is called extrapolation. Okay, extrapolation. Extrapolation is when you're making predictions in regions outside of the data. So see that the data ends at 7, starts at 2. So when you're outside of 7 or 2, that's called extrapolate, and you're predicting what the values will be based on your best fit line. That's called extrapolation. Okay, so notice that this observation here, it's kind of out of the mainstream of the pack, right? So most of the data observations are from 4 to 7. But this one is kind of, it's far away in X from all the rest. And it's having an influence on that line, because if you removed that, what we call an influential observation, if you removed it, you would get the gold line. Very different trend line, right? So with that included, you get the blue line. Take that out, and you get the gold line. So it's definitely influencing what the best fit line would be. So sometimes we may or may not want to.
When would you remove the influential observation? Or would it be?
When we're not sure if so. It depends on the situation. Like, because all the data we took from 4 to 7, you're making a judgment whether it should be there or not.
Mm-hmm.
Because all of the data we have, all the rest of the data is clumped here from 4 to 7 years. So because it's outside of that, you may or may not want to remove it. So there's not a hard and fast rule. It's going to be dependent on every situation. But you may or may not want to remove an influential observation. So you may or may not want to remove. Case by case basis. Now, there's another thing called an outlier. So suppose that we got all the data, and then we recorded all the data, we put it into the computer, and we ended up with this point 2, 30. So what probably happened here?
Maybe there's way too many cars in the market, so that you reduce price.
No. This is an error, right? What happened? Probably. From somewhere from collecting the data to making this graph, it probably was 2, 130. Right? It probably was 2, 130, but somewhere between collecting the data and making this graph, it ended up being 230. This is called an outlier. When do you remove this? Always. You don't want this in your data set. So you're always going to remove an outlier.
How do you tell the difference between an outlier and influential observation?
Because it's clearly something's wrong. It's not in the trend. You see that the influential one looks like it could be in the trend, maybe not, right? Taking it out has a great influence on the line. This outlier, clearly something's wrong. It doesn't belong in the data set, so we want to take that out. we could guess that this point was really to 130 or to 13,000, right? After 2 years, the car was worth 13,000, and the 1 somehow got removed, and then we ended up with a point 230. That's an outlier. Get it out. We don't want it. So this is the mathematics behind coming up with the best fit line that we don't have to do. But so this is what's involved in coming up with the best fit line. Lots of number crunching to get that line. You can thank me later. Tips are encouraged. Okay, so let's do some examples. 6 bears. So they're looking at a all right, so this is the chest size and weight of 6 randomly selected bears. X denotes the chest size in inches, Y denotes the weight in pounds. And use the information to complete parts A through F. Okay, so here's our data values. So they got the bears, and so we're going to use StatCrunch to find the regression equation for the line. So you can open it up in StatCrunch. Okay, so we're going to go to Stat, and we're going to go to Regression. Regression, simple, linear. Okay, so regression, simple, linear regression. That's what we're doing. Okay, and then we're going to select the X variable, which is you're going to choose the column that has your X variable. When you open it up from the actual homework assignment, those columns will be labeled. And so, or if you just open up a blank StatLab set, it'll just be like column 1, column 2, whatever. All right, so then that's Y. That's optional. Okay. So we're not doing a hypothesis test, so we can leave it marked, but that's not what we're interested in. Okay. What we want is a fitted line plot. Okay, we want a fitted line plot. I think that's all we need. We just need the X and Y variables, and make sure you click on fitted line plot. Okay, and then it gives us the least squares regression right there.
What was the F to get to the window?
Regression and simple linear. So stat, regression, simple linear. X, Y. Now those are the column headings, right? So that's because when I opened this up in StatCrunch, the column headings were already called X and Y. So you want that whatever column heading is going to be your X variable and whatever column heading is your Y. And then we want to just do a fitted line plot. And so then here is write this down, 79.202 plus 4.501 X. Okay, so we close that up. So regression equation, here we go. And it says 2 decimal places. So what did we say? We're going to round it to 79.20 plus 4.50x. Nice work. Continue. Okay, and then it gives you, and then plot the data, which of these graphs match the data and the regression line. So I'm guessing it's either A or B because we have a slope of 4.5. That means upward trend, right? Upward trend is 4.5. So I'll just guess A. But what could you do? So you actually going to plot these points and see which graph represents the points plotted on the. I think you can all do that, right? So I'm going to guess A. And that was fantastic.
I can tell by the X values because they're kind of like 40, 44.
Right, exactly. The X value,
Kind
yeah.
of like grouped together in more of a linear fashion than the other ones.
Well, these have the same X values as these. It looks like. You see that? So the X values of these points are the same as the X values for these points. See, it's really both X and Y. Okay, describe the apparent relationship between the two variables. Weight tends to increase as chest size increases. Weight tends to decrease. Weight remains constant. There's no apparent relationship. So what is this relation? What is it saying?
The weight tends to increase as chest
Right.
size increases.
That's our 4.5. That's our slope. Our rate of change is 4.5. So weight tends to increase. Where are you going? All right, identify the predictor and response variables. Okay, so that's one thing I forgot to mention. So when we just talked about X and Y, so X is called independent variable. Also, it's called predictor variable, also called explanatory. Okay, and then the Y is often called the dependent variable or response. So I should have said that stuff up front at the beginning. But so the name for that X variable, independent or predictor or explanatory. The Y value is the dependent or the response variable. Okay, so what in this case, what is our predictor variable? That's chest size. And what was our response? Weight. So predictor is chest size. That's B. Predictor is chest size. Response variable, weight. Green. Excellent. Last one. Outliers and potential influential observations. So any outliers, first of all? No outliers. Any influential observations, meaning something outside of the, it's maybe close to being on the trend, but outside of the data. Doesn't look like there's any of those either. So I would say neither of either. No outliers, no influential.
No,
Oh.
B.
I just checked the wrong one. Oh, one outlier. So I checked the wrong one. So there's no outliers, no influential. Okay, remember, 2 different sets for Sunday night. 2 different sets, the independent chi-square test, and now linear regression. And I will see you Monday.